like specific analytic, qualitative, and numeric techniques. So today is a little bit more, rather than a technique, more theoretical. How do we know that there are solutions? And if we do know that there are solutions, how do we know that there's just one? Okay, so here's a polynomial, 2x to the 5th minus 10x plus 5 equals 0. We have no technology. We're stranded on a desert island. Right? There's no general technique to solve that analytically. How do we know that, how could we know that a solution exists even if we can't solve it? Yeah, it's continuous because it's a polynomial, which means we have to be able to draw it without picking up the pencil, right? So if I can show that sometime it's negative and at another x value it's positive, then I know it has to go through 0 somewhere. So we can talk about whether or not the solutions exist without having any technique for being able to find out what they are. So if you look at this guy, if we let y be 2x to the 5th minus 10x plus 5, then if we look at y of negative 1, this would be negative 2 minus, negative 2 plus 10, which is 8, plus 5 is 13. And I think y of 1 comes out to 2 minus 10 is negative 8, plus 5 is negative 3. So we know that somewhere between negative 1 and 1, this thing has to equal 0. Between x equals negative 1 and x equals 1, the function must be 0. Has to go through the x-axis. If it was negative at some point and positive sometime, some other time, then it has to have gone through the x-axis. So this is the kind of idea that we're going to talk about today with existence of solutions to differential equations. We can talk about existence without having to have a technique of how to solve it. So the existence theorem is actually, I'm not going to prove it for you because it actually takes math like way, way above what we have. But it's a really important result. And it says, suppose f of ty is a continuous function on a rectangle in the ty plane. If t naught y naught is a point in that rectangle, then there is some epsilon, which is just a, you think of epsilon as a small positive amount, okay. And a function y of t, so that y of t solves the initial value problem on this small interval around t naught. So let's draw out what this is saying, because this is really heavy mathematical notation here. So we have a continuous function, the differential equation, right? F of ty is the right-hand side of the differential equation, has to be continuous. Okay, so if this guy is continuous, and that's not too hard of a hypothesis to satisfy. F of ty is continuous. We all know how to what continuous functions look like, how to prove something's continuous from Calc 1. So it has to be continuous for t's on some interval and y's on some interval. Morning. And t naught y naught is a point in the rectangle. So let's look at what that rectangle looks like. So I've got A to B on T, and on Y, C to D. So I've got this rectangle where my differential equation has to be continuous. Okay, so there's my rectangle. And T naught Y naught is some point in this rectangle. So I'll just put a point in here. actually. I'm going to kind of put it in the middle. Yeah. So I've got T naught, Y naught somewhere in this rectangle. The theorem guarantees then that there is an epsilon bigger than 0 around T naught. So I have some interval that I can put around T naught. T naught plus epsilon, T naught minus epsilon. Okay. So that's what this part says. The T naught minus epsilon, T naught plus epsilon is that we're making this interval around T naught. And the theorem guarantees that for some interval, it could be very, very small, but there is some interval around T naught where the function y of t that solves the initial value problem exists. So it could be, so here's my initial value, y naught, t naught, y naught. I know that there is some function y of t, at least in this small interval, that solves the differential equation. It might not go on forever, but there is at least some function in that in a small interval that satisfies the initial value problem. Okay, so the hypothesis is if the right-hand side of the differential equation is continuous, right? The conclusion is that a solution exists. It might be in a small interval, but it exists. So here's an example. I have dy dt is 1 plus y squared, and y of 0 is 0. Let's look at the solutions of this thing. It might help if we look at a slope field first. So I'm going to create one in GeoGebra. I know there's a solution by the existence theorem, because this is continuous, that satisfies the differential equation and the initial condition, but it doesn't necessarily exist for all time. In this case, it only exists on the finite interval negative pi over 2 to pi over 2.
Well, what happens after? It goes back down.
It doesn't exist. There is no function that will go through this point and satisfy this differential equation when you go outside of negative pi over 2 to pi over 2. So the existence theorem guarantees that we do have a solution, but it doesn't exist. It doesn't guarantee that it exists for all time. And in this particular case, it doesn't. It only exists between negative on an interval. In this case, epsilon would be pi over 2 if you're putting it. It's a big epsilon, yes. Yeah, the theorem only guarantees it for some positive amount. It could be tiny. In this case, it's relatively big. What the domain is? Yeah. So that's the whole idea, is that when people first started studying differential equations, finding solutions is kind of difficult, right? It takes some algebra and some thought, and people went, why are we going to try to do this if we don't even know it exists, right? If we don't even know that there is a solution. So a lot of work went into developing this theorem that allows us to know that it's there before we start trying to find it. So the theorem, I mean, I'm never going to really give you problems like find epsilon, right? But it's good to know that you can look at that and say that's continuous. I can start looking for a solution. I wonder why I have a blank slide there. I don't know. So we see that existence is not guaranteed for all t, only for some interval around the initial condition. In this case, t equals 0. And the interval was negative pi over 2 to pi over 2. open. All right, so once we know that a solution exists, how do we know whether or not it is the only one? Okay, so we found one, tangent, right? How do we know that there isn't another one? By looking at the slope field, you know, that goes like this, right? How do we know that we have found the one and only solution? Well, right. So we have another theorem that, again, lots of people have spent a lot of time developing this theorem. The proof of it is beyond the scope of this course, but the fact that it exists is going to be nice for us to guarantee that the work we're doing is worthwhile. Yeah, that has a point, yeah. So this time, we're supposing that f of t is continuous, but so is df dy. Okay, so the derivative of f with respect to y has to also be continuous. So when a function is continuous and its derivative is continuous, we say smooth and continuous. Okay? So continuous, when the derivative is continuous, sort of a mathematical shorthand for saying the derivative is continuous is to say it's smooth. Hi, morning. It is only a partial, yeah. It just has to be df dy. Why is that the only thing that needs to be continuous? Yeah, that's a good question. I don't know. I hadn't thought about it. Yeah, part of the fancy proof. I'll think about it and I'll try to answer it for next class. So if we can satisfy both of these conditions, that f is continuous and the partial of f with respect to y is continuous on some rectangle in the t-way plane, and t naught y naught again is in that rectangle. If we have two functions, y1 and y2, that both solve the initial value problem for all t in some small interval, or any interval, then we know that y1 and y2 are really the same function. For all t's in between, in some interval around the initial value. I'll draw it out. So again, we have a rectangle. A to B for t, C to D for y. So we're living inside this rectangle. So on this interval of t's and y's, f of ty, the right-hand side of the differential equation, has to be smooth and continuous. So continuous and its partial with respect to y has to be continuous. All right, and then it says, if you can satisfy that, and t naught y naught is a point inside the rectangle, t naught y naught, and y1 and y2 both solve this initial value problem, where this point has to be on the solution. So we already know by the existence theorem that a solution exists through this point in some small interval around t naught. Some epsilon ball around t naught. So this theorem says that if there are two, if you can find two functions that satisfy this, so you've got a y1 and a y2, okay, then really you can make the conclusion that y1 and y2 are the same function. So it's kind of a backwards way of saying that you can only have one. If there are two, they are the same, is the same thing as saying there can't be two. There is only one. Yes, if by parallel you mean they never cross. Yeah. Yes, absolutely. Two different solutions can never cross. Exactly, because if they share this point, right, according to this theorem, if they share a point, they are the same solution. Okay, so that is my next thing here. We'll come back to that. Yes. Yeah. Yes. Right. So it seems intuitive, and we just took our natural intuition and made it into this garbage, right? That's kind of what we do in calculus, right? We decide something has to be true, and then we go to great pains to prove that it's true and make it really rigorous. Yes. Yeah. So yeah. So your observation is that one great consequence of uniqueness is that no two solutions can ever occupy the same place at the same time. So if this ever happens, the two solutions must actually be the same. So in practical use, we can never cross, solutions can never cross. And that helps you a lot when you're looking at qualitative behavior, because if you have equilibrium solutions, you know you can never cross them. So again, this has been intuitive for us. We've been using this assumption through the whole course and not even realizing that we were assuming it. Okay. So, but now it's a good thing to have verified it and know that our instincts were correct. So what we were doing, right, is if we came up with an equilibrium solution, we went like this. And let's say we knew that this was our initial condition. We just assumed that it would, if we knew the slope was positive, right, we just assumed that it would go something like that. When really, just because the slopes are horizontal there doesn't mean we don't cross it, right? You could cross it kind of like this and have horizontal slopes. And now we know that this is impossible. Can't have, because two solutions can't cross. All right, so let's go back and do. So if you notice, both the existence and uniqueness theorems have hypotheses. That's the if part of a theorem is called the hypothesis. They have to be satisfied in order to use the conclusion. The hypotheses for the two theorems are similar. One of them says that the right-hand side of the equation has to be continuous. That's existence. And uniqueness says that the right-hand side has to be continuous, and so does its partial with respect to y. So often we lump these two theorems together into one theorem, and we just use the more restrictive hypothesis. We say if the right-hand side is continuous and so is its partial with respect to y, then there is a solution and it is unique. So we can make both conclusions at once if we have both restrictions. Only if the right-hand side is continuous and so is its partial.
Is that like something that's like it's not until it's true?
No. Nope. It could be true if it's not continuous, but it's not guaranteed. There are examples where it will not be true. This is one of them. So we have dy dt equals 3y to the 2/3. And you're right, I am using examples that have only y's in them. Because we have very limited analytic techniques, I have to choose functions that we can solve. So that's why I'm doing that, but it is true if t's are in there also. Okay, so I want to discuss the existence and the uniqueness for solutions that have this initial condition. 3y to the 2/3, is it continuous at 0? Yeah, it's continuous at 0. So 3y to the 2/3 is continuous at t equals 0, or and y equals 0. It has to be continuous at the initial condition. Now we have to check that it's partial with respect to y is continuous. But what does this tell us, right? The fact that it is continuous tells us what? A solution exists. Okay. Okay, now let's look at the partial dy of 3y to the 2/3. So I just take the derivative. 2/3 times 3 is 2. Y 2/3 minus 3/3 would be negative 1/3. So this is 2 over y to the 1/3. Is that continuous when y is 0? No. Asymptote, right? Denominator is 0. So this is not continuous when t is 0 and y is 0, which means we are not guaranteed a unique solution. There might be one, but the theorem that we've been studying does not guarantee it. So let's see what happens if we try to solve this. Well, it's autonomous. It only has y's in it, so I should be able to solve it by separation of variables. So I'm going to have y to the negative 2/3 dy equals 3 dt. Integrate y to the negative 2/3, so I would add 1 to that. So I get y to the 1/3 over 1/3, 3t plus c. Y to the 1/3 equals t plus c1, dividing both sides by 3. And then cube both sides. So I have y equals t plus c1 cubed. Use the initial condition to figure out what c1 has to be. My initial condition was 0, 0. Y of 0 equals c1 cubed equals 0. So c1 has to be 0. Okay. So y equals t cubed is a solution, right? That has that initial condition. Y equals t cubed. Okay. I claim that there's another solution. Y dt equals 3y to the 2/3. Solution 1, we just figured out was y equals t cubed. And solution 2 is going to be y equals 0. So if y equals 0, what is dy dt? 0. And if I plug a 0 into 3y to the 2/3, I get 0. So this is also a solution that goes through the point 0, 0. They both satisfy the ODE. And the initial condition. So I actually do not have uniqueness. Okay. So sometimes you don't have uniqueness. The right-hand side of the differential equation has to be nice enough to guarantee uniqueness. In this case, it was not nice enough. It's only nice enough to guarantee existence. I thought I had a picture of that guy. I guess I don't. Let's look at the slope field of 3y to the 2/3. So this guy is continuous at the point of interest. Is its derivative continuous? Yeah, it should be. We're not going to take the derivative. That would be a nightmare. But it should be, because we know that the derivatives of continuous functions are continuous. For all the nice functions that we know and love and work with all the time, they have continuous functions, continuous derivatives. So we know that the solution exists, and we know the solution is unique. Also, so my initial value, y of 0 equals 1/2, will be about right here. I know that the slopes are all positive, and I know that I can't cross the solution that exists right here, right? There's my equilibrium solution. Can't cross it, so I know that I have to follow the slope fields, and I'm going to approach the equilibrium solution without crossing it. So this is the kind of thing that we have done this already, right? We've already looked at things qualitatively and said, oh, that looks like a equilibrium solution, we must approach it, right? So we were assuming uniqueness when we did that. Now we know we have uniqueness. Okay, so here is an ODE, 1 plus t squared over 1 plus y squared with an initial condition. Show that y of t equals t is a solution to this guy. So I want you to do this in your groups. Okay, so lots of people are solving this via separation of variables, which is cool. That's fine. But I didn't mean for you to have to do that much work. I just wanted you to check that it was a solution. So by plugging in. So if y of t is t, then what is dy dt? 1. So all we have to do is check that 1 plus t squared over 1 plus y squared is also 1 when I plug in. Okay, so I have 1 plus t squared over 1 plus y squared. And now I'm going to plug in the fact that y equals t. Replace my y with a t here, so I have 1 plus t squared over 1 plus t squared, which is 1, because the numerator and denominator are the same, right? And y of t equals t is my solution, right, that I'm checking. I have to make sure that the initial value also holds here. Does y of 0 equal 0? Yeah. So y of t equals t satisfies the ODE, right? Because both sides of my differential equation are 1 when I plug in appropriately. And y of 0 is in fact 0. So we showed that y of t equals t is a solution. Now, 1 plus t squared over 1 plus y squared. Considering this function, the right side of the equation as a function, is it continuous at 0, 0? Yep, plug in 0, 0, 0 for t, 0 for y, no problem. So we're continuous at 0, 0. Now the partial with respect to y looks kind of ugly, but it's not, because you treat 1 plus t as a constant. So it's not even really a quotient rule, right? I could just do dy of 1 plus t squared times 1 plus y to the negative 2. And this just is a constant. So I bring the negative 2 down. So I'm going to need a little more room here. Negative 2 times 1 plus t squared times 1 plus y to the negative 3. And the derivative of the inside is just 1, so there it is. Which is negative 2 times 1 plus t squared over 1 plus y cubed. Is that thing continuous at 0, 0? T equals 0, y equals 0? Yeah. So the fact that the original was continuous, I have existence. The partial with respect to y is continuous, I have uniqueness. So because I have uniqueness, let's say for the same ODE, I want to consider a different initial condition, like y of 0 equals negative 0.1. Right here. We'll call this guy y star of t, the solution to this guy. The solution to it can never get bigger than y of t, than y equals t, because you can't cross solutions. So I happen to know that my slopes are always positive because I'm squaring stuff, squaring the numerator and squaring the denominator. So my slopes are always positive. So I know that the solution that has that initial condition is always increasing, but I know that it will never increase faster than y equals t, because I can't cross them. Okay. So I don't know exactly what y2 of t or y star of t looks like, but I do know that it can't grow faster than y equals t. And that may not be very much information, but we didn't do very much work to get it. And it is something, you know, like sometimes when you have a differential equation that models a real life situation, you might be interested in just how fast does it grow, right? We don't care about the exact what it looks like, but if we can bound it and say it's increasing, how fast? Well, no faster than y equals t. All right, so here is a differential equation, dy dt. I want you to study its solutions qualitatively, and you might, you know, draw a little graph, but and put in some key points, but don't make like a whole slope field. But you could put in some key slopes, like equilibrium solutions. So we start with equilibrium solutions. Equilibrium solutions are constant solutions. That means that the derivative is 0. So you start by setting dy dt equal to 0. No, wrong one. Right, and we get y equals -1 or 2. Right, so we have two equilibrium solutions, -1 and 2. So we go back and we put them in. Then you might remember these good old sign charts from Calc 1, right? So we have y plus 1, y minus 2, and the product y plus 1, y minus 2. You don't have to write this all out. I'm just showing you sort of, a lot of you did it without writing this, but I'm just putting the reasoning on paper so you have something to look at. So the zeros are at -1 and +2. So those are like our fences. Okay. Now y plus 1, when we're left of -1, so here I'm looking at the y plus 1, just the y plus 1 factor. If I plug in y is smaller than -1, it's going to be negative. So I have negatives over here. If I plug in between -1 and +2, I'm going to get positives. And if I plug in a value bigger than 2, I also get positives. Then I look at the y minus 2 factor. If I plug in a number less than -1 in for y, I'm going to get a negative. Plug in a number between -1 and 2, I'm going to get a positive, negative. And if I plug in a number bigger than 2, I get a positive. So then when I look at the product, negative times negative is positive. Positive times negative is negative. Positive times positive is positive. So because y plus 1 times y minus 2 represents my slopes, I know that my solutions will be increasing when I'm less than -1, decreasing between -1 and 2, and increasing when I'm greater than 2. So if I go back to my qualitative picture here, I know that between -1 and 2, my solutions have to be decreasing because dy dt is negative. So it's going to have to look, my solutions will look something like this. Depending on the initial condition, it could also, go something like that. And then when I'm less than -1, my solutions are increasing. So they have to come up like this. And when I'm greater than 2, my solutions are increasing also. So these have to go up like that. So I get a good idea of sort of the general behavior of this ODE without having to solve it. And how do I know that I can't cross equilibrium solutions? Because the derivative with respect to y is continuous. So this is y squared minus y minus 2 is continuous, just a polynomial, right? The partial with respect to y would just be 2y minus 1, which is also continuous. Continuous, continuous means I have existence and I have uniqueness. And uniqueness means you can't cross equilibrium solutions. That make sense? Okay. So really, there isn't anything new in this qualitative analysis that we haven't done before. It's just that now we know we're allowed to do that. So remember last class, many of you pointed out that Euler's method will accumulate error because we keep using the slope to approximate a point, and then we assume that point is on the curve, and we get a new slope to approximate a new point. It does accumulate error, okay? And sometimes it accumulates so much error that the solution we plot out will violate the existence or the uniqueness theorem. Okay, and that's sort of like a tip-off. that your Euler's method was terrible. Use another method or make delta t smaller. So here's an ODE, e to the t times the sine of y. Let's look at some equilibrium solutions. So those are places where dy dt equals 0. So I can use the zero factor property, either e to the t equals 0 or sine of y equals 0. When does e to the t equal 0? Never. And when does sine of y equal 0? Y equals multiples of pi. 0 pi, 2 pi, 3 pi. So we have the equilibrium solutions. Y equals n multiples of pi. So here's my initial value problem, y of 0 equals 5. And I'm using Euler's method with delta t equals 0.05. And I'm plotting out this solution. Okay, so I'm just going along Euler's method, delta t equals 0.05. And I'm getting this nice like curve. And you go, that kind of makes sense because it should be like nice because e to the t and sine of y are both nice functions. Get this nice curve, and then all of a sudden, a little bit after 5, it starts going crazy, right? So aside from the fact that like that doesn't kind of match up with the trend of what was happening before, I know for a fact that this plot cannot be correct. Why is that? It crosses 0, one of the equilibrium solutions. This is an equilibrium solution, and I crossed it. So I have violated uniqueness. I could say it crosses pi also, yeah. Yep. And before I can use this, though, I do have to verify. If I'm going to use that it's violating uniqueness, I have to verify that this guy is continuous and its partial with respect to y is continuous. And they are, right? Because e to the t is continuous, sine of y is continuous, so the product is continuous. And when I take the partial, you treat e to the t like a constant, and the derivative of sine y is cosine y, which is continuous. So I am violating uniqueness. Right. So I could either go back and make delta t much smaller. I could use another numerical method. Or it does appear that this might be pi, and that maybe it just continues like this, right? Getting super close to pi. So I could use a qualitative approach and say, well, can't cross that equilibrium solution. That's it.